At our next lecture, and last lecture you gone through this grid following in mostly this grid integration studies. Grid following is a classical control. Now the next emerging control is grid forming. It has several applications, and in this topic we will go through what are the generic application and what are specific to hydrogen electrolyzer, how grid forming technology can be implemented there. So this lecture will be about that. And okay, so it is over to Professor.
Welcome back. So many of the things, I mean, in the slide, probably, I already mentioned it. So maybe initially I'll quickly, go, and then maybe later when I'm going to show application, maybe I'll slow down. So again, I mean, like the previous case, this is quite similar content, but again, I mean, this is towards grid forming, and previously we mentioned like the grid following. So that would be only the difference. But as we mentioned like many times, that grid forming inverter are becoming essential components for the grid, and we talked many times that especially for like the microgrid, weak grid, and also like when you have got like renewable hybrid system where you might have hydrogen. So in those cases, I mean, it is essential that you're going to go for grid forming control for the inverter. And here actually, I mean, I did mention some scenarios where, I mean, you might need grid forming. So one of them, I mean, I already mentioned that from fuel cell produced DC, and then we need inverter DC to AC. Now in those cases, if you connect in any of these cases I mentioned, probably you're going to go for grid forming. So also let's say you have like hydrogen powered microgrid, or in those cases, I mean, you can use that grid forming control. Also, I mean, as I say, like when you have got weak grid, it support need for like to ensure stability, mainly when you have got the low inertia condition. And also another important application we didn't mention, that the black start capability, right? Mainly, let's say, I mean, if for some reason if you have blackout, right, and when you have got like this inverter dominated system, that grid forming inverter also can be utilized, I mean, for the black start purpose as well. So not only control, but also in the black start, mainly, I mean, if you that like when you have got like off grid setup, I mean, when you have got the grid setup, there are many other devices can contribute, but in off grid, as you see, like mostly renewables and converter. So in those cases, I mean, the grid forming inverter also can contribute, I mean, to restart the system as well. So the other scenario also, as I said, like the renewable hydrogen hybrid microgrid, in those cases also, I mean, when you have got like solar, wind, and hydrogen storage, all of them operate together. So in that cases, I mean, GFM can contribute not only for power delivery, but also to maintain the system stability as well. And again, it's like the advantages is that, I mean, it ensures seamless renewable energy powered hydrogen system, and also it, when you have got hydrogen microgrid, it also ensure the grid transition, because that is actually quite important. Like if you know like the microgrid, it should be having capability to operate both grid connected as well as off grid, and during this switching from connected to off grid and vice versa, there is like a huge actually transient in the system. So that time also, I mean, you must need like grid forming to ensure that transition between grid following and grid forming, and definitely it maintains voltage frequency even like in your hybrid system when you have mostly like in the renewable generation. So other scenario could be that you have like hydrogen powered backup and emergency system, where also like for example your fuel cell provide emergency backup instead of like diesel. So in those cases also GFM can ensure immediate and stable AC power during outage. And the remote microgrid for remote community, we already mentioned that could be also other scenario where you will be using GFM. Sorry, here it's in most cases we are saying like GFM, but here same thing like grid forming actually inverter, but we miss the M here. So it's again I'll correct that one. So we already I think mentioned all of them. The requirement for low inertia grid, renewable variable, block start, hydrogen power, hybrid system, and to maintain the grid compliance, we need grid forming, and in both cases they like address those scenarios by providing synthetic inertia, maintaining voltage frequency, restart grid or microgrid after outage, ensure stable operation of fuel cell, and definitely meet the voltage frequency and also low voltage right through as I mentioned. Again we already mentioned like that what is grid forming. So again I'm not gonna repeat again. So it makes the inverter act like a voltage source that leads and stabilize the grid. So it's again as you remember in previous cases we mentioned that follows, but here actually that leads, not just following the grid, and it does sets the voltage and frequency reference. So it's not like again just following the grid and injecting power to the grid. So it establishes a reference for other grid tied device. So even like microgrid, let's say you have got some grid forming, some grid following. So the grid forming one will actually provide reference to the other grid forming. So grid forming will follow the grid following like when they are like operating off grid condition. And as I said that it operates without external synchronization. In both previous cases we need external synchronization. We don't need any PLL here, and it regulates voltage frequency actively. So here as I say that this one the inverters, that's like would be the like the leading is not like the following that in previous cases that we mentioned. And here you can see that we don't need any external PLL for synchronization purpose. So that's the main difference with the previous cases. So that slide probably we already covered. No PLL required for doing the synchronization. It internally generated the voltage reference and derived from like that virtual synchronous machine voltage group and also grid forming algorithm. And it already mentioned that it operates well in isolated or grid forming conditions. So here even like in the current control loops that I mentioned previously, but here what happened like that current mode control in GFM like inverter regulates the output current based on the internally generated voltage reference. So that's actually maintaining the system stability while supporting like voltage and frequency as well. So the outer loops again that's mainly the voltage, and then the inner loop that's the current. But again that PI controllers. Again, I mean, we use even for grid forming as well, and as I said, it use most of all the devices. But the outer voltage reference is derived from like a either a virtual oscillator or like a droop control logic. It's not like coming from external grid. So that's I think the main device. But other than that, again, I mean, from like whatever getting from inner control loop, we use as input to the PWM for the inverter as input. So here, I mean, only where that's a difference like that, how we are generating the reference, but in terms of control algorithm, here also you can use like instead of current, here you can see this is a voltage source, but other than that, droop control also used here, but here also we use like PSC, which is like power synchronization control, synchro converter, which like making the converter like a synchronous generator, VSC, like also people use like meshing control, and also virtual oscillator based control technique. That's also used for GFM as well. So there are some algorithms similar, all the input is different, but some other, I mean, the new technique as well. But these are not all the techniques that when Dr. Onimesh discussed yesterday, I mean, that can be utilized here as well. But so the main things like that you are trying to mimic the characteristics of the synchronous generator. That's the like main purpose here. So like others, like droop control, again, I mean, it regulates voltage and frequency using frequency and voltage droop. VSC, it enhances the droop control by emulating the inertia and damping through the machine swing equation, which I believe all of you know. Power synchronization control, that uses active power feedback to regulate the phase angle directly. Synchro converter, that precisely replicate the synchronous machine within an inverter. So that's why name is also like a synchro converter. So it's not synchronous machine, synchro converter. And then voltage oscillator control, that actually applies like a nonlinear oscillator model to generate GFM voltage. So those are the like mostly used technique that you will find in the literature. So this one nothing to repeat. Again, I mean, that's like droop control, that trying to emulate the synchronous machine behavior by adjusting voltage and frequency based on your real and reactive power. Same technique, you just need to use or find those droop, and it's a single parameter, it's not that difficult to find it out, and then you are giving like your voltage and frequency control loop. Again, that's gonna give you your theta and voltage reference for the like inverter to operate. So in previous cases we applied, but here you can see that we are producing the reference, I mean, to from the grid. Again, I'm not going to repeat because I already mentioned that what are the advantages of droop, mainly for the simplicity. And again, I mean, in most of the cases it actually works fine. Only your droop control have problem when you have got like unbalanced situation. Unbalanced situation actually does not provide like your desired performance. So when you have got unbalanced load, and in microgrid, in other cases you could have unbalanced load, and also like if you have a microgrid or like weak grid, and if you have a like a not like symmetrical fault. I believe you know symmetrical and unsymmetrical fault, right? So when you have got fault like in 3 phases, we call it symmetrical. But if you have fault like one line to ground or line to line, in those cases, I mean droop control performance is comparatively poor. So if you see like your system that you are working on is not actually balanced, then you will go for other control technique. And when your system like heavily nonlinear, fixed droop coefficient may not handle all grid condition as like a PI control. So you might need to change the droop coefficient when your operating condition changes significantly. And other problem also in many cases it's provide steady state error, like both frequency and voltage deviation. Always our expectation that steady state error should be 0, but that's also like problem. But there is a way that actually you can enhance the droop control technique as well. Not like that you have to always use that like standard power, frequency, voltage, reactive power. So you can have like adaptive droop, which is going to provide variable droop based on your system condition. So it's going to change the droop parameter. Also, droop parameter is like a primary control, right? You could also have like a secondary control. That secondary control going to give the reference to the droop when the system condition change. That's how your overall microgrid or whatever situation you have, even using the droop plus secondary, sometimes you also have tertiary as well, but up like up to secondary in most of the cases is fine. So using that secondary control layer, I mean you can restore like the voltage and frequency when your only droop fails to do so. You can also like integrate with virtual inertia, predictive control, and other either communication less or communication assisted, like centralized, decentralized. I'm not going that far because it's not like a control course, but using like both centralized, decentralized, or even like recent year also you have got distributed as well, because the centralized, decentralized both have their advantages as well as limitation as well. Because centralized, what happens like you have to collect signal from all the devices you have, then you process your control, and then using communication again you have to send back the control signal to all individual devices. So when you have got multiple devices and if your communication is not reliable, for example, let's say communication fails, then you cannot give signal back or even collecting the signal from that well. So that time your system performance might deteriorate. But also decentralized, you don't need communication, but the problem is that, for example, here if you have got one electrolyzer and another electrolyzer is other location, they cannot communicate, they cannot talk with each other. So they only know what is happening in a particular location. So only based on the local control signal, it will produce the control action. But the hybrid, so the distributed, it use some communication, but only communicate with the nearby devices. So for example, you are here, you only talk who is your like a left and right. Someone like quite far from you, you are not talking with you. But the next one, he is like talking with the next body somehow. So we have got some limited communication, but at the same time, it doesn't need to collect signal from everyone. So people are nowadays also doing like distributed as well. So again, but that's for mainly the secondary level control. So VSC, although we talked for the previous cases as well, but again, the way that we are designing slightly bit different based on the signal that we are using here. So as I say, like the from the droop, you're gonna get those like input, and then you're gonna apply in your VHG control. Now how we can design this one? Again, based on these two simple equations. So this one, that swing equation, and this one is just like your internal EMF in the synchronous generator. Now synchronous generator also, you know that sometimes we model first order, sometimes we model second order, but also you can go like fifth order, seventh order as well, but depending on your requirement you go. But for this sort of control, first order, second order is more than enough. So by just using these two equations, you can actually you can see here, sometime you are adding, sometime you are dividing. That's how you are just implementing this equation, and then at the end, when you have got d omega by dt, and then you are doing that integration, that's how you will getting your omega. So our here our intention to get omega, and here our intention to, because that's the variable, that's the voltage, internal voltage. So once you rearrange this equation, put everything in the left hand side and put all our other side, and then if you just develop that block, you can easily develop this two block, and that's how you're gonna get your the angle and voltage which we need for your grid forming inverter. And as it is using like damping, inertia, droop coefficient, that's how it's gonna be trying to mimic the characteristics of the synchronous generator. So the PSC, the third one, that again synchronizes the inverter with the grid by regulating the power flow rather than tracking the grid voltage. So here again you see that by this angle it's gonna be synchronizing, but it's not, it's not following the grid angle which is does for grid following inverter through that PLL. So it actually producing that angle, that gonna help to synchronize with the grid. Now the controller again, that's you see that compares active power, and then by using that's like a integrator, it producing that theta, and then finally from that it gonna be giving the command to the grid forming inverter. Now here it's just the comparison, these three so far we have talked, which one provide which function. So for example, the grid forming, islanded operation, inertia emulation, in terms of also complexity, which one is good for weak grid. So this is again this one like PLL based, which is grid forming. So that's why you see many cross here. But normal like the PSC one that we talked about, again we did not use that swing equation, so it cannot actually emulate the inertia for the system, but these two can service like the other operation that's needed. So the one that I mentioned, that synchro converter, that exactly emulate the full dynamic behavior, not only swing equation, because if you remember VSG, it only takes the swing equation, but for this one it tried to emulate the full dynamic behavior of the synchronous generator using that power electronic converter and the control logic. So that's the biggest difference. So although here again as I mentioned, depending on what sort of model you're gonna use it. So as I said, like it might be like sometime you can go up to like a fifth order model electromagnetic. So if you go like all the equation that you're gonna be coming here, you have to use all of them, and through that, I mean, at the end, I mean, you will be developing all the block at the end. From that, you're gonna get your power, and then you're gonna be applying again for that things that we mentioned from your inertia. So the inertia things coming it here, but all the voltage equation you're gonna be solving, and then that's how, I mean, at the end you're gonna be getting the power. So from that, it is a little bit complex, but it's not that you cannot do it. So you just need to first think like that, what sort of synchronous machine model you're gonna use it, and then based on that you're gonna write those equation, and then from that you will be finding power, and then, I mean, from that, I mean, you can, and then our desired signal again, I mean, that omega theta, and then we're going to apply that one to the converter. So here again says that, I mean, it's not only like electromechanical, that's only for damping and swing, but also like electromagnetic, which actually does involve internal voltage and current dynamics, because we are trying to capture like flux, linkage, and also rotor interaction. So to do that, actually you have to go for higher order model, and also this inverter computes like virtual torque from power deviation, then integrate to obtain the virtual rotor speed angle, and then use it to generate the voltage waveform that you can although, I mean, we haven't shown all the step here, because it's going to take like long space. I mean, if you want to show how you can rearrange the model, but the thing is that you just need to rearrange the model. That's, I mean, you have to do it. So again, as I mentioned, that it does consider everything that you will be seeing in the synchronous, like rotor inertia, swing, internal EMF dynamics, governor, turbine, excitation system. So everything that's part of the synchronous generator that you're going to be considering to provide through this synchro converter, virtual rotor dynamics, all that happening inside the damper winding, mechanical input frequency, because the governor mechanical, this one normally does regulate. Normally in synchronous machine we use like AVR, automatic voltage regulator, that also be included here in the synchronous converter as well. But on top of synchronous machine, sometimes it's also include like FRT for providing low voltage right through support for the converter as well. Now other one, as I mentioned, like meshing control. So the meshing, again, I mean, both like meshing control and also like voltage oscillator control are PLL free for the grid forming inverter, that enable inverter to generate voltage and frequency autonomously, that support to establish the grid. And also this is like a decentralized, you need like, you don't need like communication as well. So meshing control is therefore designed to utilize the device level similarity between power converter and synchronous machine. This is like, again, between these two, they actually try to like mimic the behavior. So that's how they actually mesh with these two, just to provide like provide the grid voltage behavior. And the other one, voltage oscillator circuit. So here, without like using any PLL, it emulates like a nonlinear oscillator circuit to generate like a voltage waveform. From that one, we generate that voltage waveform, the oscillator, and then we apply like across multiple inverter using that inherent oscillator coupling. So that's how, I mean, it produces the voltage and then we use for GFM. Now, in terms of application, again, I mean, we already mentioned many times that it can be used. We already mentioned that hydrogen system, but also, I mean, we already mentioned that this one already many grid. Even in Australia, we do have number of grid forming BS already in operational. Renewable, it might happen in coming years, but so far they concentrated only for battery. For the battery, I mean, this is could be that architecture we might use. If again, I mean, this is, you see, this is again that swing equation. From that we got theta v, which is producing reference from inner control loop, and then through PWM we apply your inverter to generate whatever voltage and frequency we want. But it can be used for hydrogen system as well, not only the battery, although the battery is already using. But here you can see that's how probably that's how we can use for hydrogen, like from hydrogen production. If you use DC and then DC to AC, then I mean you can use that one, and this could be like simple control, but other controller that's also mentioned. It can be applied for hydrogen based system, which might be, although it's not happening now, but it might be working as grid forming control in coming years to provide that grid stabilizing service it might need when you have got large scale green hydrogen system will be connected, grid connected. So, if you have like separate off grid system, that's defined, but when you have got large scale, definitely grid will also provide requirement that unless you provide that grid ancillary circuit, you will not be allowed to connect with the grid. So, but that's actually I mean possible. So, this one showing one example that if you want to do it for fuel cell system, that's how I mean like here like two parallel system that's having SOFC types fuel cell with like grid forming control. So, that's how I mean you can design then, and if you are working in this area, probably you can try I mean this sort of architecture as well. So, as I said in coming years, maybe you will not have a single system, you will have a multiple system. So, you can consider not only single type fuel cell, you can also use different type fuel cell that we mentioned previously, because definitely it's not that all the installed system would be PM, although that provide better performance, but you will having the other system as well. So, it's good to do like several scenario analysis that I mean you can do it, but here just showing like one example that also you can do. So, again I mean we already mentioned what are the key advantages. So, black start, if your grid impedance is high, grid is weak, and then you want to emulate inertia, and then for islanded operation as well. That's we already mentioned that weak grid it cannot handle. Now, that GFM have already been deployed, as I say, like in many application already. So, it's not only that's now like a research, already like in the implementation phase, but having said that, still I mean there are many work has to be done I mean to get exactly the behavior that we are expecting to get it from grid forming inverter, stepping, because this is just like self-explanatory. You can do that, but in Australia, I mean, we have a number of project that already really implemented in the power grid. The inverter type they have used, but as I said, all of them have the battery, and all the project they have got function like this one, providing like the fast frequency response, because in Australia like we already have frequency ancillaries market. So if let's say if you own the battery, and when the market need it, and if you participate in the market, at the end whatever service you're going to provide, you're going to be paid back. So that's already happening. So the and many project that people are doing, they are not only using the battery to store energy and provide power during the peak time, but they also sometime participating in the market and making money. So that's how, I mean, all the battery is expensive, but that's how probably when you have got multiple application, I mean, you can make sense that it's not only technically but economically feasible. But if you just, I mean, think about single application, then battery is still expensive device. But when you consider like multiple application, then I mean, it will make sense that you have battery. So in Australia, as I say like that, there are also many company for virtual power plant. So if you just make contract with them, you're gonna be also paying monthly, whatever the agreement you have through battery. That's how also you can make money, but at the same time you are also helping the grid as well. But on top of that, you are also making money. And this other project for islanded operation battery, and then this one mainly to provide synthetic inertia and fast frequency response as well. And this one is more like the storage for grid stability. Again, I mean, how I'm going with the time. So again, I thought like because last time one of you mentioned like to showing the comparison between battery, but this one like because the fuel cell electrolyzer more of the load, right? It's not generating any power, so you can just control the input power like as a control load. But here like when you have got electrolyzer, it does produce electrical power. So here like in this simulation just shows like that when that you need to, for example, let's say maybe I know you are asking to provide additional power. Now how, but now here this is like the hybrid system. This is not simulation like separately battery and fuel cell. So what that showing that when you have a hybrid system and there is a need, and you have got both battery and fuel cell, so how both of them are responding. So definitely here you can see that which one is performing better here. You see that the battery response is quicker, right? Because if you see here, sorry, so whenever need is immediately almost like exponentially is giving the power, but here slightly but why it is going, because that time, because this sudden support we need only during the transient, because here we have a grid, right? Later I mean the additional support, and when also you have got power from fuel cell, so battery is again, I mean, we don't even want to utilize that time. So battery power is again like going from discharging to might be negative, that means it's going to charging phases. But what I'm trying to say that if you have a like a hybrid system, sometime I mean it's gonna be giving better service. Although I showed one example, but here also the same system, like when your SCR is less than 3, you see that the system collapse is going like unstable, but when you have like grid forming, it's again going back. But grid following, it cannot do not only that system. In most of the system, when having that SCR low, you might have problem. So again, this is like a very hot topics. Not only like in Australia, I know many countries now they have so many work is going on. In Australia, you will find most of the power industry now their main focus like how we can improve that performance that we are getting from grid forming inverter. So again, machine learning and that AI or reinforced learning, that's always like hot topics in different area. Several people like droop control or VSM, that's I mentioned. To tune that parameter, you can use that one. Hybrid, how like GFM and GFL working together. So for example, let's say if you have 100 inverters, how many you need GFM, how many need you GFL? What should be the ratio? Still, I don't think there is any like established method that you can say that I need 5 GFM and 10 GFL. So still, how you gonna use it? How you gonna coordinate them? When you have got 100,000 of them, how you can operate together? So and also what are the different topology for inverter and what are the different mesh system? You have got radial power system. So depending on like different things, there are still many works that need to be done. So here actually I put number of research question. I'm gonna share with you. So those of you are interested, this gonna be give you enough to think on what actually you can do. If you are really interested to work in the, I could discuss, but if I want to do one by one, it might take another hour. But I think the research question is given, how to find the answer, that would be research. But sometime finding the research questions for those of you are doing PhD, it takes 1 hour to do the literature review, finding the problem, and then asking the exact question. That once you have the answer, you will have something new that gonna contribute to improve the power system performance. But at the same time, you can also publish, you can improve your track record, and that gonna be crucial for your future career as well. So I'm gonna leave it with you to read, and if you have research scholar or if you work by yourself, you can pick up anything that messes with your expertise and also with your future research direction as well. With that, thank you. Hope now you have got some idea like how this grid following, grid forming works, in which situation you're gonna be use what type of inverter, what type of control, right? And then as I say, although I didn't discuss, but that's gonna give you some things to think about, and then going from here. Thanks for your time.
Thank you, Professor. So we'll take questions afternoon. So all of you are requested to leave for lunch. So 2:15, please gather here. We will have a photo session.